Welcome to today's lecture. Today we will have a tutorial session. We will solve multiple problems where we have single phase systems without reactions. So, some of these problems would be similar to the ones which we did during our exercise problems where we discussed these concepts. Here we will perform more problems so that we can actually get more familiarized and be comfortable with solving such problems. So, here is the first problem. The radiant energy incident on the earth's surface on a sunny day is roughly 900 watts per meter squared. Collecting and focusing sunlight and using the focused beam to heat a fluid is an old idea, and as the environmental costs of fossil fuel combustion mounts, solar heating has become an increasingly attractive alternative. Suppose a house is to be designed that will have a circulating forced air central heating unit and solar energy is contemplated as a heat source. If air is to be fed at a rate of 1000 meter cube per minute at 30 degrees Celsius and 1 atmosphere, and the air is to be heated to 55 degrees Celsius before being discharged into the living space, what is the required area of the solar collector panels? Assume 30% of the radiant energy incident on the plates is used to heat the air. So, here we are asked to design a solar panel. So, we need to identify the area of the solar panel based on the amount of energy, the heat which can be transferred to the air, also accounting for the efficiency of such panels. So, let us try to see how we would solve this problem. So, this problem is reasonably simple for the fact that we have only one component and it is a very simple heating process. So, we will have to first look at whether there are any material balances that are required. Here we have been given the volume of air which is coming in. So, we need to convert this volume into moles so that we can use that for calculating change in enthalpy rather than change in specific enthalpy. So, now for calculating the amount of air which is fed, converting the volume to moles, we will use ideal gas law. According to ideal gas law, PV equals nRT. So, here P is 1 atmosphere which is equal to 1.013 times 10 power 5 pascals, and volume is 1000 meter cube per minute, and R would be 8.314 joules per mole Kelvin, and temperature is 303 Kelvin or 30 degrees Celsius. So, this is the condition of air which is entering into the solar heater. We can calculate N. So, here it will be N dot because it is molar flow rate. N dot would be equal to PV divided by RT. So, we have V dot. So, it will be PV dot equals N dot RT. So, we are calculating N dot as PV dot divided by RT. So, 1.013 times 10 power 5 times 1000 divided by 8.314 times 303 will give you the number of moles per minute. So, this value is 40,212.1 moles per minute. Since the energy which is solar energy is given in terms of watts, it would be useful to convert this particular term of molar flow rate into moles per second. So, this would mean molar flow rate N dot equals 40,212.1 divided by 60 moles per second, which is equal to 670.2 moles per second. We have air coming in and leaving the system, which means this is an open system. So, the energy balance equation is Q dot minus Ws dot equals delta H dot plus delta Ek dot plus delta Ep dot. So, here there are no moving parts. So, shaft work could be 0. So, there is no change in kinetic energy or potential energy that has been given to us in the problem. So, we would have Q dot equals delta H dot. So, we just have to calculate delta H dot. So, delta H dot is equal to N dot times delta H cap. We already have calculated N dot, we just need to calculate delta H cap. So, delta H cap is equal to integral Cp dt and temperature here increases from 30 degree Celsius to 55 degree Celsius. So, we can look up the tables or any handbook to get the Cp of air. So, Cp of air with Celsius as the units would be 0.02894 plus 0.4147 times 10 power minus 5 T plus 0.3191 times 10 power minus 8 T squared minus 1.965 times 10 power minus 12 T cube. So, integrating this Cp from 30 to 55, you would get delta H cap value as 0.728 kilojoules per mole. So, we now have delta H cap. So, we can calculate Q dot, which is equal to delta H dot as N dot times delta H cap, which is 670.2 times 0.728. So, this gives Q dot as 487.9 kilowatts. So, 487.9 kilowatts is required for heating air from 30 degree Celsius to 55 degree Celsius. We know that the solar panels are only 30% efficiency. So, because they have only 30% efficiency, we need to account for that. So, the amount of solar energy which is actually required would be solar energy required would actually be equal to Q dot divided by efficiency, which is Q dot divided by 0.3. So, 487.9 divided by 0.3, giving you the amount of solar energy required as 1626.4 kilowatts. We have been told that 1 meter squared can actually provide 900 watts of energy, solar energy. So, which means we can convert this total solar energy required and use this to calculate the area of the solar panels required. So, area required would be equal to amount of solar energy required, which is 1626.4 kilowatts divided by 0.9 kilowatts per meter squared. This would give us the area required as 1807 meter squared. So, we would require 1807 meter squared of solar panels for the given problem, so that we can heat air from 30 degree Celsius to 55 degree Celsius. So, the amount of air heated would be 1000 meter cube per minute. So, with this we have actually solved the energy balance problem, and we will move on to the next tutorial problem. So, here is the next tutorial problem. In the manufacture of nitric acid, ammonia and preheated air are mixed to form a gas containing 10 mole percent ammonia at 600 degree Celsius. The ammonia is then catalytically oxidized to form NO2, which is absorbed in water to form nitric acid. If ammonia enters the gas blending unit at 25 degree Celsius at a rate of 520 kilograms per hour, and heat is lost from the mixer to its surroundings at a rate of 7 kilowatts, determine the temperature to which air must be preheated. So, here we have some information about heat being lost in addition to what we need to supply. So, we need to account for this while we are performing the calculations. So, here we have also been asked to calculate temperature. So, if you look back at some of the one of the problems which we did during the lectures, we have actually solved such equations to get temperature. So, here we will again apply the same principles. So, let us look at how we can solve this problem. First thing we need to identify is the composition of the air is given as 10 mole percent, composition of the gas mixture is given as 10 mole percent ammonia. So, we need to convert the mass of ammonia which has been given into moles, so that we can actually use them directly. So, and also we have Q, which is lost to the surroundings, heat lost to the surroundings in terms of 7 kilowatts. So, the flow rate should be converted to per second instead of per hour, With these things in mind, let us first convert 520 kilograms per hour to moles per second. So, let us first convert 520 kilograms of ammonia per hour to moles of ammonia per second. So, this would be 520 kilograms per hour using the molecular weight of ammonia, which is 17 grams per mole. So, you would have 1 mole weighs 17 grams, and we can convert kilograms to grams using 1000 grams are present in 1 kilogram times 1 hour contains 3600 seconds. Now, kilograms get cancelled, grams gets cancelled and hours gets cancelled, and you would end up with moles per second. So, the units you have is moles per second, and the mass or the moles of ammonia which is coming in is 8.48 moles per second. So, the basis for this problem would be 8.48 moles of ammonia per second. So, using this basis, let us now draw the flow chart for the system. We have been told that there is a gas blending unit where you have one feed which is ammonia, that is 8.48 moles of ammonia coming in per second at 25 degrees Celsius, and there is another stream of air which is coming in. We do not know the number of moles of air which is being fed. So, let us call it N1 moles of air per second, and we also do not know the temperature at which it is coming in. So, we will call that T degrees Celsius. We do know that the final mixture is going to have 10% ammonia, so which is 0.1 ammonia and 0.9 air. So, this is the condition of the mixture, and we have also been told that the temperature of this mixture is at 600 degrees Celsius. We have also been told that there is heat lost, which is Q dot equals minus 7 kilowatts. As heat is being lost from the system, we will take this as a negative term. So, the number of moles which would be leaving this system, we can call it as N2 moles per second, which would basically be the sum of the moles of ammonia and air which is entering the system. So, now that we have this flow chart, we need to first perform material balances to get some of the values which have to be calculated. We will see whether material balances by themselves are sufficient to do this, and then we will proceed further. To identify if material balances are sufficient to get the flow rates, we need to perform a simple degree of freedom analysis using only the material balances. Here we have two components, one is ammonia, other is air, which means we can have two independent equations. In the given system, we have two unknowns which are N1 and N2. So, this means that the degree of freedom is 0 for the material balance problem in our hand. So, we can perform simple material balance calculations before we start the energy balance calculations. So, the material balance calculation would be ammonia which is coming in at 8.48 accounts for 0.1 times N2. So, from here we can calculate N2 as 84.8 moles per second. Now that we have N2, we can write an air balance or a total balance and get N1. So, total balance is basically 8.48 plus N1 equals N2. So, we already know N2. So, we can calculate N1 as 76.3 moles per second. So, now we have the molar flow rates of ammonia and air and the mixture which is leaving the system. We now have to calculate the temperature at which air is being fed to the system. For this, we need to perform energy balance calculations. First thing we need to do is to identify whether this is an open system or a closed system. As we have air and ammonia flowing in and out of the system, this is an open system. So, we have the energy balance equation as Q dot minus Ws dot equals delta H dot plus delta Ek dot plus delta Ep dot. So, Ek and Ep go to 0 because there is no change in kinetic and potential energies. There are no moving parts, so Ws goes to 0. So, Q dot equals delta H dot is the energy balance equation we end up with. So, now we need to calculate the delta H dot. So, we can calculate delta H dot for the inlet ammonia and the outlet mixture which is leaving the system. However, we cannot calculate the enthalpy of the air which is fed into the system because the temperature is not known. However, the equation using this can actually be used to calculate the temperature from that. So, let us see how we would go about doing this. So, we already know that Q dot for the system is minus 7 kilowatts, which is minus 7 kilojoules per second. So, we need to now calculate delta H dot. So, in terms of the temperature of air which is being fed and solve for temperature. So, for this we need to build an enthalpy table. So, the enthalpy table would contain substances N dot in, H cap in, N dot out and H cap out. So, here you would have ammonia and air. So, ammonia entering the system is 8.48 moles per second and air entering the system is 76.3 moles per second. This is the same values which are leaving the system also. So, we need to identify a reference state for which this table can be built. So, the reference state which we use can be based on the inlet or the outlet conditions. So, let us assume the reference states to be the outlet conditions. So, if we were to use that, then you would have ammonia gas 600 degrees Celsius and 1 atmosphere and air at 600 degrees Celsius and 1 atmosphere as your reference states, which means the outlet condition enthalpies would be 0. So, the inlet enthalpies have still to be calculated. So, you would have H1 cap and H2 cap. So, H1 cap would be equal to integral of 600 degrees Celsius to 25 degrees Celsius Cp of ammonia dt. So, this would be a numerical value which you can calculate. Using the Cp value of ammonia, this can be calculated as minus 25.62 kilojoules per mole. So, the next step is to calculate H2 cap. H2 cap we cannot calculate the numerical value because we do not know the inlet temperature. So, our problem would be given as H2 cap is equal to integral 600 degrees Celsius to temperature T Cp of air dt. So, we have already identified the Cp of air for the previous problem as well. So, we can actually use this Cp and end up with a polynomial which would be a 4th order polynomial of temperature. So, using the Cp of air you would end up with a 4th order polynomial for this equation. So, H2 cap would then be integral 600 to T Cp of air, which is 0.02894 plus 0.4147 times 10 power minus 5 T plus 0.3191 times 10 power minus 8 T squared minus 1.965 times 10 power minus 12 T cube, and this would be dt. So, this would be solved by integration to get the 4th order polynomial. So, now this 4th order polynomial can be brought in to calculate delta H cap, delta H dot. Delta H dot would be equal to minus 8.48 times H1 cap plus 76.3 times H2 cap. So, with this particular equation we can substitute it back into the general energy balance equation we had, which was Q dot equals delta H dot. So, Q dot, which was identified as minus 7 equals minus 8.48 H1 cap plus 76.3 H2 cap. So, from here we can solve for the temperature using the fourth order polynomial which we arrive. So, that would be temperature of 691 degrees Celsius. I am not going to go into the details of the integration and how the polynomial is going to be solved. I expect you to practice it and actually be able to solve it on your own. So, please do try to solve this and confirm whether you are able to get the same temperature that I have arrived at, which is 691 degrees Celsius. Here is the third tutorial problem. A waste heat boiler is a special type of boiler that generates steam by removing the heat from a process that would otherwise be wasted. In your company, the stack gas from a furnace where a gas mixture containing 90 mole percent methane, 5% ethane and 5% propane is burnt completely with 25% excess air, enters the waste heat boiler to produce steam. This steam is used to sterilize a bioreactor. The stack gas leaving at 1000 degrees Celsius is cooled to 500 degrees Celsius in the waste heat boiler. There is no heat lost from the waste heat boiler to the surroundings. All heat is used for the steam production only. If 100 moles of fuel gas is fed to the furnace, calculate the amount of heat that is lost by the stack gas in the waste heat boiler. Calculate the amount of saturated steam at 40 bar that can be produced from 50 degrees Celsius feed water for the same basis. At what rate in kilomoles per hour must the fuel gas be burned to produce 1500 kilograms of steam per hour, the amount required to sterilize a bioreactor in the waste heat boiler. What is the volumetric flow rate in meter cube per hour of the gas leaving the boiler? So, now we have a problem where we are asked to calculate the amount or masses of substances. So, here we can actually perform these calculations, but first we need to look at the material balance which is required. So, although we are worried about energy balances only for the waste heat boiler, the feed to the waste heat boiler is from a furnace, and this information is required so that we can have the information about the gases which are present in the gas which is entering the waste heat boiler. So, we first need to perform material balances which will help us identify the composition of the gas which is being fed to the waste heat boiler. So, let us start performing the material balance calculations first. The fuel gas which is burnt in the furnace contains methane, ethane and propane. So, all these are burnt to produce only carbon dioxide. We have been told that it is complete combustion. So, no carbon monoxide would be formed. So, we first need to write down the combustion reactions for this particular system. So, you have methane reacting with oxygen to form carbon dioxide and water vapor. So, balancing this equation we would get 2O2 and 2H2O. So, similarly the balanced equation for combustion of ethane would be ethane plus 3.5 oxygen gives 2 CO2 plus 3 H2O, and for propane it would be for 5 O2 it forms 3 CO2 plus 4 H2O. So, we are asked to assume a basis of 100 moles of fuel gas. So, we will do that. So, basis is 100 moles of fuel gas. So, this would contain 90 moles of methane, 5 moles of ethane and 5 moles of propane. We have been told that 25% excess air is supplied. So, for that we need to know how much air is actually required, so that we can calculate how much air was actually supplied. So, we know that for 90 moles of methane would require 180 moles of oxygen for complete combustion. 5 moles of ethane would require 5 times 3.5, which is 17.5 moles of oxygen, and 5 moles of propane requires 5 times 5, which is 25 moles of oxygen. So, total oxygen requirement would be 180 plus 17.5 plus 25, which is equal to 222.5 moles of oxygen. We have been told that air is supplied at 25% excess. So, we can assume that air is 21% oxygen and 79% nitrogen. So, you would have air required as 222.5 moles divided by 0.21, which is 1059.5 moles of air. So, air supplied would be 25% excess of what is required. So, which would be 1.25 times 1059.5 moles, which is equal to 1324.4 moles. So, nitrogen supplied would be equal to 1046.3 moles, which is basically 79% of the total air, and oxygen supplied would be equal to 278.1 moles. The stack gas composition would not just contain oxygen and nitrogen, it would also contain carbon dioxide and water vapor. We have also been told that the reaction goes to completion, which means none of the hydrocarbons are actually present in the stack gas. So, the stack gas will only have carbon dioxide and water vapor. So, to calculate the moles of carbon dioxide, we will use the stoichiometry, and 1 mole of methane produces 1 mole of carbon dioxide, and 1 mole of ethane produces 2 moles of carbon dioxide, and 1 mole of propane produces 3 moles of carbon dioxide. So, writing a balance for carbon dioxide, we would actually have output equals generation, there will not be any consumption terms or input terms, and that steady state accumulation goes to 0, giving us output equals generation. So, output would be equal to 90, which is the number of moles of carbon dioxide generated by combustion of methane, plus 5 times 2, which is the number of moles of carbon dioxide generated by combustion of ethane, plus 5 times 3, which is the number of moles of carbon dioxide generated by combustion of propane. So, the total number of moles of carbon dioxide present in the stack gas would be 115 moles, and similarly we can do the calculations for water, and output for water would be 90 times 2 plus 5 times 3 plus 5 times 4, giving us the total number of moles of water as 215 moles. So, we already know how much oxygen is fed, we also know how much oxygen is consumed during these reactions. So, we can calculate the output for oxygen as input minus consumption, which would be 278.1 moles minus 222.5 moles, giving you 55.6 moles. Nitrogen does not take part in the reaction. So, whatever is coming in would also be leaving. So, output for nitrogen would be 1046.3 moles. So, with this we have the composition of the stack gas which is entering the waste heat boiler. We know that this stack gas is coming in at 1000 degrees Celsius. So, now our next step is to perform the energy balance calculations for the waste heat boiler. So, since all these gases are combustion gases, we can actually use tables from the textbooks or from reference books where we can get information about the enthalpies for these gases. Table B8 in Felder-Rousseau, which is one of the prescribed textbooks, actually has these values, and we can directly use them for performing these calculations. So, for using that table B8, we need to use the appropriate reference state. So, the reference state used for that table is gas 25 degrees Celsius and 1 atmosphere, and this would apply for all the components in the system. So, the components you have would be carbon dioxide, water vapor, oxygen and nitrogen. So, you would have N in dot, H cap in, N out dot and H cap out. N dot N for carbon dioxide is 115 and for water vapor is 215 and for oxygen it is 55.6 and for nitrogen it is 1046.3. So, the output of the furnace, which is the stack gas, is the input for the waste heat boiler. So, the composition of the stack gas which we calculated as the output has been used as the input in these terms. Inside the waste heat boiler there is no reactions. So, the number of moles of any of all these components will still remain the same. So, the outlet condition would also have the same components, 115 moles of carbon dioxide, 215 moles of water vapor and 55.6 moles of oxygen with 1046 moles of nitrogen. So, we now have to find out the enthalpy values for all these terms. So, you have carbon dioxide and water vapor, oxygen and nitrogen all entering at 1000 degrees Celsius. So, all these values have to be looked up the enthalpy table for combustion gases. So, if we were to look up these values are given as 48.6, 37.69, 32.47, 30.56 and 21.34, 17.01, 15.03 and 14.24. So, this gives us the enthalpy table. So, now that we have the enthalpy table completed, we can perform the energy balance calculations for this open system. Your Q dot is equal to delta H dot. So, because there are no moving parts in a waste heat boiler, so shaft work goes to 0 and kinetic and potential energy changes are also 0. So, Q dot can be calculated as delta H dot, which is equal to 115 times 21.34 minus 48.6 plus 215 times 17.01 minus 37.69 plus 55.6 times 15.03 minus 32.47 plus 1046.3 times 14.24 minus 30.56, giving us Q dot as minus 25,626.4 kilojoules. So, this is the amount of heat which is lost by the stack gas in the waste heat boiler. The next part of the problem asks us to calculate the amount of saturated steam at 40 bar that can be produced from 50 degrees Celsius feed water for the same basis. So, now we need to perform the energy balances for the water. So, whatever this heat is lost by the stack gas would be gained by the water which is being fed at 50 degrees Celsius, and we have to calculate it as the outlet condition as saturated steam at 40 bar. So, for part B we can use steam tables, and the H cap of water liquid at 50 degrees Celsius can be looked up the steam table to get 209.3 kilojoules per kilogram as the enthalpy with reference to its reference state in the steam tables. And similarly, H cap for water vapor at 40 bar, which is saturated vapor at 40 bar, is 2800.3 kilojoules per kilogram. So, these values can be obtained from the steam tables. So, the total change in enthalpy, specific enthalpy for the water which is coming in at 50 degrees Celsius and leaving as water vapor saturated at 40 bar would be 2800.3 minus 209.3, which is 2591 kilojoules per kilogram. So, now the energy balance for this equation for this system would have been Q equals delta H cap delta H dot, Q dot equals delta H dot, and we have to calculate delta H dot. So, delta H dot is basically m dot times delta H cap. So, we know that the heat which is gained by the steam would be equal to the heat lost by the stack gas. So, Q is equal to 25626.4 kilojoules, and delta H cap we just calculated to be 2591 kilojoules per kilogram. So, your m dot, which would be mass of steam generated, would be 25626.4 divided by 2591, giving you a value of 9.89 kilograms of steam per 100 moles of fuel gas burnt. The final part of the problem requires us to calculate the rate at which fuel gas must be burnt to produce 1500 kilograms of steam per hour. So, here we already calculated that 9.89 kilograms of steam can be produced per 100 moles of fuel gas. So, to calculate the amount of fuel gas which needs to be burnt to produce 1500 kilograms of steam, we would just have to perform simple calculations, which would be 1500 kilograms of steam can be produced by 0.1 divided by 9.89. So, 0.1 is the number of kilomoles of fuel gas burnt divided by 9.89 times 1500, giving us 15.17 kilomoles per hour. So, 15.17 kilomoles of fuel gas has to be burnt per hour to get the required steam output, which is 1500 kilograms per hour. We have also been asked to calculate the volumetric flow rate for this. So, using PV dot equals N dot RT, we can calculate V dot, which is 15.17 kilomoles per hour times 8.314 times 10 power 3 joules per kilomole Kelvin times temperature is 773 Kelvin, which is 500 degrees Celsius, divided by pressure, which is 1 atmosphere or 1.013 times 10 power 5 pascals. So, V dot would be equal to 962.4 meter cube per hour. So, 962.4 meter cube of fuel gas has to be burnt per hour for us to get 1500 kilograms of steam with the given conditions. With this, we have performed enough energy balance calculations for systems which do not have any reactions. So, even the phase changes which have happened, we have only used steam tables. So, we have not accounted for phase changes explicitly. So, in the next few lectures, we will look at phase change operations and how the energy associated with phase change has to be accounted for while performing energy balance calculations. Thank you and goodbye.